All right, so I'm going to try to talk about trees and ADTs in as little time as possible. So what is an abstract data type? The idea is that so far I've sort of just been writing functions to do some computation, to get some value out of the list, to do some math, right? Now we're actually going to try to represent real objects, real ideas, and real things using code. Okay? And a key principle that we want to follow is data abstraction. So abstraction says that when I'm driving a car, I don't need to worry about how someone decided to implement the inner circuitry of a car, how they decide to implement the mechanics of the car or physics. I just need to know how to use the car. I just need to know how to use the steering wheel and how to use the gas pedal, right? So I shouldn't have to worry about how my car was implemented. I just have to know how to manipulate my car. And the idea is that now we're going to sort of use code to represent these abstract things like a car, right? So let's say I want to represent siblings. And on the left here, I have one implementation, one particular wiring of a car that uses a list. On the right, I have another implementation. This uses a dictionary. And the idea is that I don't care about those implementation details from the perspective of the user, right? That's all hidden away behind the abstraction barrier. I just need to know how to use my car. I just need to I just need to know how to use my constructors and my selectors. So all those details are abstracted away. I could have gone with the left side. I could have gone with the right side. Both of them work for what I want to do. Okay, so yeah, we're going to abstract away the implementation details. That is the idea of the data abstraction and the abstraction barrier. So we're going to use this notion of data abstraction to build a representation for a tree, right? Let's represent a tree in code. And so what is a tree? A tree is a collection of nodes. Every single node is going to have a value at that node, and it's also going to have a list of branches. A branch of a tree is all of the nodes that compose, that are like the descendants of a tree down a particular path. So for this tree, it has two branches. It has this left branch, which is itself a subtree of our larger tree. And then we have the right branch, which is also another tree. And these two branches compose a list of branches. And sort of using just a label and a list of branches, I can compose an entire tree, right? Because I'm going to have my label at the top of my tree, and then I'm going to have a list of branches. Each of those branches are a subtree, so they're going to have more trees in them, and that's how we create this sort of nested tree structure. Okay. At the top of my tree is my roots, and at the bottom are my leaves. Okay. So it's very important that I have subtrees within a larger tree because now I can recurse on those subtrees. Right. So how is a tree implemented? This isn't too important because these are implementation details that are abstracted away. But we have constructors and we have selectors to get values out of a tree. And what a tree is under the hood is just a bunch of lists, right? So when I build a tree, I'm concatenating a label onto a list of branches. A list of branches is a list of trees, and trees are objects. So therefore, this list has a bunch of pointers to tree objects, right? And so this is my label. It's at the front of my list, and these are my branches. To get the label, I call label selector. To get my branches, I call my branches selector. A common misconception is that the branches of this tree is just 2 and 5. No, it's the entire subtree, not just 2 and 5. It's 2, 3, 4, and then 5. And then isLeaf will just return whether a node is a leaf. Okay, so how do I actually move through a tree, right? How do I iterate through a list? So let's say I have a simple problem statement. I want to return whether or not my tree has a 5. Okay, so we're going to implement the search function, and the workflow is that I want to start at the top of my tree. If I'm searching through a list, I'm going to start on the left and go to the right until I have nothing left. If I'm searching through a tree, I'm going to start at the root and then advance further and further down into my tree, which are, again, subtrees of my larger tree. And once I run out of trees to go through, once I'm at a leaf, I know I can stop. Right. So we're going to start at the top. I want to perform some computation. I'm going to ask, hey, are you 5? If you are, great, I can just return true. If not, I have to advance further down into my subtrees. How do I do that? Well, I know that a tree only has 2 attributes. It has a label and has branches, right? So I better use branches. What is branches? Branches is a list of subtrees. So how do I iterate through a list? I can use a for loop. And I'm going to iterate through every single subtree within my larger tree for every b in branches of t. And then we're going to perform some computation on them, right? I want to search through all of my subtrees. So how do I search through a tree? I know how to search through a tree. I just recursively call a search on those trees. We're going to make the recursive leap of faith, assume my search function works, and call search on my subtrees. So this is a very common solution that I got today. And this is actually not exactly right. So let me try to share my Actually, it's going to be hard. I can't get my iPad to work. So let's just think about this, right? If I just return search of b of x, what is that saying? It's saying for each branch, right? Branch in blue, branch in yellow. For each branch, I'm going to return this result of a search. So I start at this left branch because we start at the front of my list. So I'm going to start at the left branch and search for a 5. Is there a 5 in here? There's not. So I just return nothing, right? Because when I'm iterating through my list, you're only returning the search on the first branch. We're not waiting until I get through all of my branches because there might be a 5 hidden on later on. Okay, so this is wrong. So I don't find an x in my first subtree in this blue region. So we never even look at the second, right? That's the issue. So here's another potential solution. Is this one right? So this is saying if I get down all the way to the bottom and I reach my leaves and I still don't find my x, then I know like I can return false, right? Because I've gone all the way to the bottom and I haven't found my x. Well, this still suffers from the same problem. This base case is better, I guess. It's more comprehensive, but I'm still returning the result of the call only on the first subtree, right? Okay, so I mean, you know how to solve the problem, find x in a list, right? You have to iterate through the entire list and look for that value. We can't just return whether or not the first value of my list is equal to x, okay? So what we have to do is I have to go through my entire list and impose an if condition on each element. If one of them happens to be true, then I will return true, else I'll return false, okay? And this is a very common workflow for a tree problem. All right, so this one was Boolean, so I could have aggregated all my results together using n-ary, right? I'm saying if I find an x in any of my recursive calls, I can just return true, okay? So in this case, it's a Boolean, so we're using a Boolean aggregator like any or all. But for example, a different problem might ask you to sum all of the labels in a tree, right? In that case, you would sum a bunch of recursive calls, okay? So we're going to perform recursive calls on all of our subtrees, and then we have to worry about aggregating the results of each of those recursive calls together. Okay, so let's work through an example together. So this example is called n-ary. I want to return whether or not a tree is n-ary. And I should probably try to get screen share my iPad to work. So give me 1 second. Okay. So I'm saying a tree is n-ary if each one of its subtrees have a target number of branches. It has n branches. Okay. Not including leaves. Leaves are automatically n-ary. So something like this is n-ary because every single subtree has 1 branch, 2 branch. Is that the same for this subtree? Yes, it has 1 branch, 2 branch. Therefore, this is n-ary. Sorry, I really don't know how to use this. Or sorry, in that case, it was binary, right? So if I called it with n is equal to 2, then it would return true. All right, let's say n is equal to 3. What is a n-ary tree with n is equal to 3? Well, that could look something like this. Okay, so this would return true because every single tree has 1 branch, 2 branch, 3 branch, and this one also has 1, 2, 3. This has 1, 2, 3, and this is a leaf, so it's automatically true. Okay, whereas something like this does not return true for n-ary of n is equal to 2 because yes, this has 3 branches, but my down here there's only 2. Okay. absolute mess, but let's get back to the code.
Okay, for whatever reason, the recording stopped when I changed screens. I don't really know why, sorry about that. Okay, so let's implement n-ary. So let's use what they tell us, right? A leaf is automatically n-ary, which is sort of a weird definition, but I mean, I guess it makes sense because I'm saying all of my non-leaf nodes. So my leaves are excluded from this n-ary definition, so we don't really care about how many branches they have. So if I'm at a leaf, then I can just return true. Next, I'm sort of checking whether or not every single subtree within my tree is also n-ary. So therefore, if I want all of my subtrees to be n-ary, if I can find a single tree that's not n-ary, then I can short circuit and return false. Okay? So I'm going to say num. So how do I get the number of branches when I'm standing at the top of my tree? At the top of my tree, I can figure out how many branches I have by calling len on my branches, right? Because len is a list of trees. So if I call len on it, that will tell me how many subtrees I have. It's not going to tell me how many nodes are under me. It's just going to tell me how many sort of different paths I can fork down into. And then if this number is not equal to my target n, then I can short circuit and return false, right? Because then I know not all of my subtrees have n branches. Okay, if I do not pass my base cases, then what do I have to do? I have to advance further down, deeper into my tree. How do I go deeper into my tree? Again, remember 4b and branches of t, super important. This will allow me to access each of those subtrees that are nested within my larger tree. And I'm not going to make the mistake of returning n-ary on those branches, right? Because that will just go down my first subtree and return whether or not it's n-ary. No, I have to go through every single branch. And how do I do that? Well, instead of just returning the result right away, I'm going to impose this condition on every single subtree. And if a subtree turns out to be not n-ary, then I can short circuit and return false. Else, return true here. No, right? I have to wait until I've exhaustively searched through my entire tree. Only then can I conclusively say, hey, since none of my subtrees are not n-ary, then therefore my entire tree is n-ary, okay? And we can simplify this down into one line using return. I'm going to do a list comp of n-ary of bn for bn branches of t. And then what do I have to do? I want all of my nodes to be n-ary, so I'm going to call all here. Okay. And that seems to work.